So this is going to be our second video in this section 9.3, where we're going to look at the inference and the confidence interval part. So we're going to look at how to do a confidence interval hypothesis test for regression data, like doing the scatter plots essentially. So math-wise, this is probably one of the easier things you have to do because all of the math is more or less done for you. It's just going through a few of the formalities. So the first thing we're going to do is do a confidence interval. This wants us to do 95%. Oops, a 95% confidence interval, as we see right there. So let me write the formula for that. The formula is the slope. The slope is going to be B1. Okay, little b1, that's going to be important. I didn't go into detail about this. I usually do that, but I don't think I ever did. But realize that b1 is the slope plus or minus your critical value with n minus 2 degrees of freedom times the standard error of b1, or the standard error of the slope. So b1 plus or minus t star n minus 2 times the standard error of b1. So this may look a little confusing at first, but I'm going to show you how not confusing this really is. So we're going to look back at the table here once again. We have a lot of stuff here. Anytime you see sum of squares, this is called an ANOVA table. If you see F ever, we're not going to look at ANOVA tables. You can just cross that out. Okay, you never need to look at ANOVA tables. Just ignore it. So that part we're going to ignore. The dependent variable, sometimes it's listed up there, so that's always nice. We know that y is minutes. We talked about r squared and s already, so those are important. You'll notice right here, this table actually gave me degrees of freedom. Notice how it's 14 minus 2 is 12. Remember I wrote down here n minus 2, n was 14 apparently. So it's 12 degrees of freedom. This one gave it to us. We move down here. We know that this is the LSRL. It would be y hat equals 4.16165 plus 15.5088x. And now we're moving on to the rest of the table. All this stuff here is going to be important for this video today. These aren't. Oops. The ones that I'm crossing out are not, but the bottom ones there are all important. So that's the new part of this video here. So let me make this hopefully crystal clear for you. So recall that, remember, this is the slope. Okay, that is your slope. It's with the variable. It's not the constant. Remember, this is the y-intercept. We don't really care about that right now. We care about the slope. So B1 is the slope. That means in my formula we have 15.5088 plus or minus. All right, so we already have that. Now we need to find our critical value. So we know the degrees of freedom is 12 because it told us. If that wasn't there, somewhere it would have to say that they did 14 phone calls. This problem does not because it's given to me there. Whatever your sample size is, in this case 14, you just take away 2 from that. So I'm going to put up a link to a T-star calculator. This is, I think, the easiest one that I found for you to use. So all you're going to have to do, okay, on the site is go to degrees of freedom, which type it in is 12. Remember, 14 minus 2 is 12. Type in your confidence level, which I believe we're doing 95. Yep. Do 0.95, hit calculate. And the important thing here is always use the two-sided t-score. Okay? Don't use the one-sided. Use the two-sided. The two-sided is the correct critical value for that. So if you just type in the confidence level and the degrees of freedom, look at the two-sided and it will give it to you every time. So pretty easy there. You don't have to remember the half of what's outside, so that's kind of nice. And it's making it positive for you, so there you go. So 2.1788 is our critical value. So 2.1788. And then I just need the standard error of B, but notice up here we have SE of coefficient. That is the standard error, SE. And we're looking at the slope. So we don't care about anything in the y-intercept row right now. All that's yucky. This is the standard error of the slope, 0.505. It's that simple, ladies and gentlemen. It is that simple. That's the equation. So at this point, all I have to do is type it in my calculator. So let's do it. Do 15.5088 minus 2.1788 times 0.505. So our lower is going to be 14.409. 14, I don't know why the eraser is there, 0.409. And then we just need to do it for the plus one. And maybe there's a way to get the old answer back, but I don't know. So I'll just do it again, 15.5088 plus 2.1788 times 0.505. And I got 16. And my answer is gone. There we go. And I got 16.609. So 16.609. And that is the intercept. Or not the intercept. That is the confidence interval for the slope. So what we're doing is we're trying to make an interval where we think the true slope is falling. So the B1 is not the true slope. This is not the real slope. Remember, this is just a guess. This is an estimate of what the slope is. We don't have every single data point that exists, so we're making an estimate. So what we're saying is that the real slope is somewhere in here. So to interpret that, we would say I am 95% confident that the true slope between the length of the call and the number of components repaired is between 14.409 and 16.609. And we're just not going to put the units, so we don't need to worry about it. Just put what the slope is, and there you go. So I'm 95% confident the true slope between the length of the call and the number of components repaired between 14.49 and 16.609. Is that straightforward, ladies and gentlemen? It's a matter of you being able to read the table and you being able to use the inverse T calculator. Okay? So we're going to do that one more time. Then we'll go back and do the hypothesis test, which requires even less math. So this was the example with the sparrows, their weight versus their length, wing length. We have a different table here. This one is not giving me DF. There is no DF. We have the analysis variance table down here. That's your ANOVA table. This is the no-no, so don't. The DF is there in this example, but don't rely on that. Okay, so that is actually, no, it's wrong. So ignore that. No, I think it was right. It doesn't matter. In this problem, they are actually telling me the sample size of 116. So the DF is going to be 114 because 116 minus 2 is equal to 114. So there's your DF. I think it actually might be on here. I'm just going to double check. So yeah, your DF was there, but people get confused about looking at this. Don't know which number to look at, so don't worry about the ANOVA table. Just ignore it. So that's how you can find the DF if it's not given to you. So 114. So our slope in this problem, remember, we don't care about the y-intercept column or row right now. We only care about this one. There's our slope, 0.4674. So 0.4674 plus or minus, I need to find my critical value. So remember, DF is 114, and they want us to do a 99% confidence interval. Okay. So DF was 114. 0.99. Always look at the two-sided. Our critical value is 2.6196. 2.6196 times the standard error of the slope, which is right next to the slope. Remember SE coefficient, 0.03472. 0.03472. And all we have to do is type that in, and we are done with our confidence interval. So let's go back to our calculator, do 0.4674 minus 2.6196 times 0.03472. So there's our lower for the slope. 0.376 is fine. Let's do the upper. 0.4674 plus 2.6196 parentheses 0.03472, and the upper is 0.558. Okay, so we're ready for our interpretation. So we would say I am 99% confident that the true slope relating the weight and wingspan of, specifically a type of bird, sparrows, Savannah sparrows. Savannah sparrows is between 0.376 and 0.558. There you go. That is how you do confidence intervals. I am 99% confident the true slope relating the weight and the wingspan of Savannah sparrows is between 0.376 and 0.558. So that is the difficulty of confidence intervals. It's you being able to look at the table and pull stuff out, essentially. So that's the first half. The other half is going to be us looking at hypothesis testing, which once again is not overly difficult. That's what I wanted. And I'll delete this. So for the hypothesis test, what you're doing is, once again, we're looking at the slope. We're trying to see, is there actually a relationship, a linear relationship between the two variables. So to do that, we just need to know what to look at the table. I'm going to sneeze, hold on. So there's one last thing we need to look at this table. And that is this stuff right here. You'll see t-ratio and you'll see prob. T-ratio is the t-score of the hypothesis test. The prob is your p-value. So everything is given to you right off the bat. So we're going to go through all the steps. It's just we don't have to do any math. We just have to go through the steps. So step one, I know it's been a while. We skipped it in square, but in this one we have it back, and that is define the parameter. So the parameter for this test, remember the slope, the sample slope was B1. The parameter is beta 1. So remember, we usually use our letters for statistics, and we use Greek letters for the parameters like mu and sigma and all that jazz. So beta is for the slope. So we have to define our parameter. For simplicity of reading, I'm going to type, but I'm going to type out beta 1, but you should probably just write the symbol. Okay, the symbol right here. So we're going to, I don't know why it's not giving me my text box. There we go. So we're going to let beta 1, or don't write beta 1, actually write like beta right? Beta 1, okay? If you're not sure what a beta, if you don't like my betas, you can Google beta, Greek letter beta, and they'll give you maybe a better look of it. So let beta 1 be, it's not going to be perfect, but it's all right. Let beta 1 be the true slope relating. This one was about relating the time of the call and the number of components prepared. Step 1. Step 2 is HOHA. This is going to be super easy for you because HO and HA is never going to change. We're always going to do two-sided tests here because that's what the output almost always does. So HO, whoops, HO is going to be beta 1 equals 0. Okay, we're always going to assume that there is no relationship. If there is no linear relationship, then the slope is 0. It's just a horizontal line because it's a blob. And HA is always going to be beta 1 is not equal to 0. Because the output almost always does two-tailed tests. This question, we weren't supposed to do a hypothesis test, so I'll just make my own alpha 0.05. Okay, so we did step 1, step 2, step 3 and 4 were the t-score and the p-value, but I got some news for you. They're right here. Your t-score is here and your p-value is here. So all you have to do is write the t equals 30.7, p-value is equal to, or is less than or equal to 0.0001. And it's always a good idea to write DF because we're not doing that notation that we usually do. So DF was 12. So because we don't have the probability that t is greater, less than, or all that, it's important that we write the DF. Okay, so the p-value is less than any alpha that we're ever going to use. It's less than 0.05 definitely. We don't know what the p-value is, but we know it's less than 0.0001. So if it's less than 0.0001, it's going to be less than 0.05. So this is going to be reject. So we're already ready for the conclusion. This is how quick this is. So since my p-value is less than alpha, I reject HO. There is evidence, and we're not going to say there is evidence that the slope is not equal to 0. We're just going to say there is evidence of a linear relationship between the, oh, this is not the bird one. This is, okay, the length of the call and the number of components prepared. Okay, so since my p-value is less than alpha, I reject HO. There is evidence of a linear relationship between the length of the call and the number of components repaired. And we just did a hypothesis test without a calculator because the computer software, remember, this is supposed to be computer software. We're just putting the output here. This already did all the math. The computer did all the math for us. This is how real stats is done. The computer spit a bunch of stuff out, and your job is to be able to read and pull out the information you need from that output. We did it. So we find a parameter. It's always going to be beta 1. We did HOHA. We found the t-score and the p-value. We threw the DF in there to be safe, and we wrote our conclusion. So we'll do it one more time, just so there's no confusion here. Let's see, I have another example. Delete this. And it's gone. All right. That was weird. It's kind of gone. Okay, so this one we're using a significance level of 0.01, so they gave it to us. Remember, we can ignore the ANOVA table. This is not the pen. This is a no-no. What we need is right here. P-value is 0.000. Just means it's tiny, so it doesn't really matter. We just know it's little. So first step is to define your parameter. So let's beta 1, and then I'll switch to typing now. So let beta 1 be the true slope relating the weight and wingspan of savanna sparrows. It doesn't matter if you write X, Y, Y, X. That does not matter. You could write wingspan and weight. Doesn't matter. You HO, HA. So HO. HO. It's going to be beta 1 equals 0. And then HA. It's going to be beta. Whoops. I was doing a mu there. It's going to HA is going to be beta 1 is not equal to 0. Find our t-score and p-value. T-score, 13.46. P-value, just write equals 0.000. It's fine. So t equals, I forgot already, 13.46. The p-value, I'll just put equal to 0.000. And the df was 114. Remember, we found that because we had 116 sparrows, and 116 minus 2 is 114. So this is obviously a reject scenario again. If it was failed to reject, you just say failed to reject, and there is no evidence of a linear relationship. So let's write that out. Since my p-value is less than alpha, I reject, oh goodness, HO. There is evidence of a linear relationship between the weight and wingspan of savanna sparrows. And there you have it, ladies and gentlemen. That is how you do a hypothesis test and a confidence interval for this type of data. I hope you see it's pretty straightforward. It's kind of nice for us because we don't need to use a lot of calculator stuff, so it's not as tedious as some of the other things we've had to do online. It's just a matter of being able to read it and to know what to pull and then how to do it. Hopefully this helps. This will probably be the last video that I do. We are getting close to the end, so hopefully this is helpful for you. Remember, if you have any questions about anything, please feel free to ask me, and I will answer those for you as soon as possible. All right, thanks for watching, and we'll talk to you later.